at this point in time, there were 15 like this, which were pre-flight types of computers used for hangar queens at the spacecraft and various simulators, a lot of simulators for training the astronauts and to check the software, that kind of thing. So this kind of computer was used then. And they were built without encapsulating any of the modules. Unfortunately for us, we can, as a result of that, when we get this thing open, you can see the insides and see how this thing was constructed. The flight version would be all encapsulated and just look like a block of metal. So there were 15 of these, and there was something like 42 or so actual flight types. Now, one thing is interesting here. In the slide, you see that that is a gold color, and this isn't. So you can ask the question, why? And as near as I can find out, I asked Klein Fraser yesterday because it wasn't clear to me either why the difference. As I remember, they were all supposed to be gold for thermal reasons. Gold does not radiate and absorb. It's the best color to have for radiation and absorption. And the idea that all of the thermal transfer had to be through the frame and into a cold plate that was mounted in the spacecraft, rather than radiating into some other environment and other equipment around the spacecraft. Now, Klein informed me that production computers, or flight-type computers, got changed fairly early in the program because of a corrosion problem, which I might mention later. It's a problem with the metal, and it got painted with epoxy, as you see this one. Now, why this one got painted, I have no idea, because I would assume this one should be gold color. Just because at the time that this one was built, I didn't think we knew that we had to go to the other color, or the other. But that was beyond my memory at this point. The ROM failed or something of that sort. Now, another thing of interest here is, what is this thing? And next slide. Here's the property transfer records. My dear friend here got this computer from a junk dealer, and he can fill you in more on that if you like. And here's the property transfer record that he has that accompanied it. But of interest here is the date of this. I don't know whether you can see it or not. It's not very clear. But the computer was transferred from 1975. Somebody right up there at the top in 1975. This tells me that after the program was finished, Delco, which was responsible for putting all of the guidance system together and delivering it to NASA, had that computer and transferred it back to the government. Another point of interest here is the price, $275,000. That might be kind of earth-shaking in today's terms, but when you realize at that period of time, even the integrated circuits in here probably cost anywhere between $30,000 to $50,000, just the purchase price of it. So the purchase price of the components that went in here probably ran close to $100,000. And then, of course, you had to do all the rest of this that you see here. Now, the next slide will show you where this thing sits in the spacecraft. This is a picture of the internal guts of the command module during assembly. And it's what's called the lower equipment bay that you see right here. The computer's right here. A disk is right up there. And optics, which was a second type of function, is right at the top. And right in there, in that yoke, is where the inertial measurement unit sat. And there's other electronics here associated with the servos and so forth that run the IMU here. But there's the essential part that we're talking about. So that's where this device sat in the command module. There are pictures on the web of how they're mounted in the LEM also, if you're interested in that. And there's one disk in the LEM. So in the command module, there's two diskies. Later in my slides, I have the slide of the diski on the main panel. Now, as I've mentioned, there was 42 of these produced at Raytheon. Raytheon was the manufacturer of the flight types. Now we will proceed to try to take this thing apart and see what we see inside. We've taken out a lot of the screws, so we don't have to sit here all day while we're cranking out the screws to put this apart. We have to take out a few more yet. As the previous speaker said, there's two trays here. We'll hold that part down. Good, we got lots of qualified technicians here. I hope they have their union card.
My ESD training is out of certification.
We all have union cards. Okay. Now, you saw the previous speaker had a slide similar to this. That shows what we're looking at here. Now, maybe what we should do is just sort of raise these up so you get a view of it. This one on this side is what was called the logic tray, and on the other side is the memory tray. And as you noticed here, there's two rope modules plugged in the front, which we'll remove later. And there's a capacity for 6 there, as indicated in the previous speaker. Now, starting with the memory tray, there was an oscillator here, and it ran at a fantastic rate of 2 megahertz. Next to that is the alarm module. You heard something about the alarms, but one of them, which I will mention here, I'm quite positive in this alarm module, is the power failure detection. We had to detect the power. If the power was failing, we had to detect that so that we could conserve the erasable memory. And if you young people remember, Apollo 12 got hit by lightning as it was taking off, and the computer survived several power transients during that period of time and maintained its memory. Now the IMU tumbled, which means it lost its coordinates, so the computer didn't have the proper state vector because the IMU wasn't given it the right information. But the computer worked through those lightning. And since the command module is sitting right up there on top, it got the biggest blast from the lightning. So the alarm module does that kind of thing. Then let's remove now one of these sub-assemblies to see what we're going to see. We've got the erasable memory modules here to your right. The erasable memory itself is a black object in the middle. Then over here on the moving across are 2 sense amplifier modules, one for the erasable memory and one for the rope memories. And then electronics that operate the ropes. And they were all constructed using what was called welded cordwood construction. Again, this is a technology which I guess has gone down the drain. I don't know how many of you realize what this is, but in that slide there, it sort of gives you an idea of how these are assembled. You have a metal frame here with a bunch of holes in it. You have electronic components that fit in these assigned slots, transistors and transformers and that kind of things, and the big ones, then resistors, condensers. And then those are all interconnected point by point with weldable wire and then welded on each end. So it's very labor intensive to assemble that thing. Part of the reason for the cost. Now, let's take out one of the sense amplifiers. And what you see in that slide is one of these sense amplifiers, one of the 2. They're both more or less identical, but since the characteristics of the erasable memories and core memories are obviously different. The parameters of the two sense amplifiers have to be slightly different. So you see it's the same kind of construction. Now of interest here is probably one of the first, if not the first, analog type integrated circuit operating as a sense amplifier. Right in here it was, the chip itself was in a TO8 type transistor can with 8 leads. And you can see this if you look up closely at circuit. As you see, it's the same construction, all welded cordwood. Now let's take out the erasable memory. Now unfortunately this erasable memory is encapsulated, so we don't actually able to see the core stack. But as you've already heard, this erasable memory is 2048 16-bit words in a coincident current type operation.
I just want to make a remark.
Okay.
As my job as curator, that's the one question I get asked more than any other one is the memory of the Apollo computer and how it compares to some everyday object. And I think my Casio watch is about 2K if you figure out the kind of number of characters stored. So that's obviously it's not the same, but it's the same ballpark in terms of. But it is the one question I'm asked more than any other.
Well, that's 2K buried down in there. That's a Faraday core coincident current type memory. And this is read and write, whereas the ropes are ROM type memory.
Eldon, did you talk about the access time of the memories?
Well, I hadn't planned to. Yes. The memory cycle time for the computer is 11.7 microseconds or 11.4. Do you remember, Ray?
Like that.
Something like that.
11 something, yeah. 11.72, I think.
11.7.
Okay.
Give or take.
He's always worse than the rest of us. He's got to get it down to the right microseconds. In that period of time, 11 microseconds, the computer would read a word from the memory and then restore it back. So I don't know how long it was that the erasable memory was faster than the core memory, the ROM. So I think the cycle time was selected as a result of the speed of the ROM, wasn't it?
Yes, that's what I remember.
It was more or less limited by the read time of the ropes. So we could have operated the erasable memory faster than that. Does that answer your question, sort of? Okay, let's see. We've got the rope now. E-memory. Yeah, we were going to take out one of the rope electronic modules. You'll see the same thing, but we'll just take it out and prove it to you, because you might doubt what we're doing here. And I've already mentioned, but in this in these early computers that we're talking about, everything is not encapsulated. As a result, we're able to see all this beautiful stuff. Otherwise, you wouldn't see anything in these modules except like the rest of them. That's the only kind of thing you would see, which isn't very exciting.
Eldon, what's the encapsulation material?
Well, it was a very lightweight foam. I don't know the details of which foam it was at this time. Now, the erasable memory had it different. The stack itself, of course, being a coincident current memory, well, nobody has a picture of it, and I don't, but it's laid out on the table before it like this, something like this, and you fold all this thing up into a little pile of cores about like so, that would fit inside of here. And those had to be encapsulated with a different kind of material, otherwise it would crack the cores and stuff, and that used some sort of a rubbery kind of material. And we had to change that at one point because the vibration, when the computer went into vibration, the core stack would actually vibrate and it was breaking some wires. That was very early. So we had to come up with a material that was still soft enough not to break those little ferrite cores and still strong enough not to get in vibration and break the wires. So that was quite an exercise to do, but it was still a soft kind of material that the core stack was potted in. And then that would fit in here, and then there was a few diodes and stuff that was going here. And then it was all finally encapsulated with this foam material that I mentioned, which of course was supposed to be quite light. But as you see, that's pretty heavy too. If you... Oh, here, I've got to remember my duties here. I got the proper union card, but I can pick these up and look at it. And he has the one that takes to unscrew them. So you see the same thing. Individual transistors and resistors and diodes plugged through here and wired both sides. And then wires coming down and going to the outside pins. So all of this was of that nature. Now, let's leave that for a moment. We'll get back to it, but I want to get over here to the logic tray, and we picked this up short, but we'll look at it again, sort of like this. Obviously, this is the same kind of construction. These are two power supplies. The computer had an input of 28 volts from the spacecraft, and these power converter modules, actually, these take the 28 volts. One of them generates 14 volts, the other one generates 4 volts. And those three powers were the only ones used in the computer. That was a very hotly contested point, too. Lots of engineers like to have lots of different power supplies between here and there. But sort of dictated we were only going to have two. 14 volts was mainly for the electronics here that had to drive the various memories, and the 4 volts is for the logic in this tray. And then the 28 volts was used in the diski for operating relays and so forth. I'll mention that later. So as you see, these are the power converter modules. Then right here are 5 I/O type modules, and we'll be removing one of those. And this is the I/O connector for the system. And over here is a test connector for ground checkout, but for a flight type computer there was a special module on here that had logic in it and would detect if the computer had any burps and store that so that it could be downlinked on the telemetry or to test equipment if it's on the ground. So this had a special module for flight. Then the rest of these modules in here are logic, and we'll go on to those in a moment. So let's put this back down and start out with the interface module. Let's see, what we were going to do is take one of these, right? As I mentioned, there's 5 interface modules, 2 different types. The one that he's removing, there's 3 identical ones like this. And one reason why we're removing this one, it has the only analog to digital converter in the computer. It took inputs from the spacecraft's hand controller and converted it to digital. And the hand controller didn't really need very much accuracy, so it was a very simple kind of analog to digital converter, and it's just part of the electronics right down in here. With that red thing is a transformer that's set in there. The rest of the interface was, well, I won't get into too much detail, but almost, well, everything was transformer coupled for electromagnetic compatibility, EMC, and that kind of problem, to make sure that there weren't we don't disturb other electronics or they don't disturb us. They were all transformer connected for the interfaces. The other two will look just like that, but won't have the analog to digital converters. Now let's take out a logic module. That one right there you want to take out? Well, probably, as you've heard many times, and we've seen already today, that this is one of the first actual mission-type computers that used integrated circuits in the history of man. And somebody said someplace that, I guess Ray said that yesterday, that in 1964 or something like that, he said, what did you say, Ray?
Well, what my memory is that Minuteman was about a year and a half ahead, and they had a whole bunch of types of integrated circuits.
I object. We were a year and a half ahead of them.
That's we were at the end, a year and a half ahead.
In the beginning.
The beginning too, no?
Yes.
I remember reading about the integrated circuits.
Yeah, right. The literature tells you the other way.
Right.
But if you look at the records, the Apollo computer was about a year and a half ahead of Minutemen or any other program.
And working, in fact, and having something working.
Having working
Yes.
hardware with integrated circuits. Now, Minuteman flew before we did, because we had to wait for the astronauts. Mine's affecting the
No, I'm not objecting. I just want to, since the Minuteman stuff's not going on, I want to add one thing. The Minuteman flew first, I think it was 7 out of 9 flights flew, and they had minor problems. They all exploded. And the reason they had the problem was that they had these particles in their integrated circuits, and at staging, they would cause a short and the thing would blow up. And the way that got sorted out was we had the same problem on these circuits a year or two before, got figured out what the problem was, how to screen for it, how to get rid of them, and the Minuteman people then picked up all that technology, even went to Raytheon to get them to do it. So the Minuteman integrated circuits computer was successful by picking up on that piece of manufacturing technology.
Thank you, Klein, for that plus. Well, we actually took out two modules, but of interest is this one, which I wanted to point out. On one side we got black little gadgets, on the other side we got these nice gold ones, except for these down here. Now, the reason for that is these black ones were manufactured at Fairchild. And Fairchild supplied quite a bit of micrologic in the early computers and in the design phase, but they got interested in bigger and better things that you guys were interested in, and went away. As a result, we fortunately were able to buy equivalent part from Philco Semiconductor, and they went out of business after the Apollo program, fortunately. But these gold ones on here then were delivered from Philco Semiconductor, and almost all of the flight hardware integrated circuits were delivered from Philco. Now, we had many other vendors. Texas Instruments delivered quite a few early in the program, but they, like Philco, got interested in bigger and better things, so went away. And if Philco hadn't been dedicated enough to stick with us, we would have been in trouble. So this is the... Oh, another thing I wanted to say. Just a moment. Excuse me a moment. I've forgotten something. I've got to get to my battery.
Hook up that power.
It's 28 volts or...
We talked about block 1, that's the block 1 logic tray, and this is a block 1 logic module. Sort of equivalent to this, except this has double the number of logic gates, And if you see, it's actually a little bit smaller. So Moore's Law was in effect before Congress even passed Moore's Law. The other thing about it, this is a little bit smaller than a factor of 2. See, there's 240 gates in here and 120 in here. So that matched very well, the logic module. So Moore's Law was okay. But this is a little bit smaller than Moore's Law. And that difference was made up because this is using a multi-layer board that the integrated circuits are mounted on. Over here, the equivalent interconnection between the logic had to be done by welded cordwood construction. What else? And that took more space. So the technology changed from this kind of construction to multi-layer boards made up the difference. So I wanted to make sure you realize we proved Moore's Law here. Okay. Oh, now he's got a slide up there. That's the gate from Philco. You can tell by their little, that means it's a Philco gate. And this was their dual 3-input RTL NOR gate, which is what the computer used. Which is also a technology that's completely obsolete now, as far as I know. I don't think anybody uses that kind of technology. Next slide. And then you see where did I put that? Well, anyway, you see the various logic gates here. Down here, a multi-layer board. These get mounted on there and then put into the frame there. If you go to the next slide, you see those different breakdowns. Okay, now I guess we will go back to the memory tray. The next thing we want to do, isn't it, is take the ropes off, right? That's what we want to do. Sure. You may hear more about how a rope works, but I think Ray's going to mention something about it. But in effect, it's nothing more than a transformer. If a sense line goes through the core, it'll get a 1 when you switch that core. If it doesn't go through the core, it gets a 0. And it's just as simple as that. So in designing or putting the software into the memory, you have to thread these sense lines either through a core or not through a core. So this schematic here sort of explains that. And you've already seen this picture. The final result of this thing, unfortunately we can't take it apart to show you, but the previous speaker had a better slide than this. But you see the cores there. In the module this size, let me get to the literature here so I don't make any mistakes. It has 512. We use tape-wound cores for the ropes, in contrast to the ferrite ones in the RAM. Tape-wound cores, there's 512 of them, and 192 sense lines. But obviously not all that 192 went through any one core because some of them are zeros. But anyway, 192 sense lines gave you a total of 6,144 words in this size memory. Now, that's kind of, well, we won't go into that. Modern day is a little different than that, as you know. Yeah, that's what you got right there, yeah. Now, let's continue. Did you get both ropes out?
I just got one
Oh.
on that. You want to take both of them out?
Well, I guess we can. Yeah. Yeah. Yeah, as you can see here, there's room for 6 ropes here. The computer will run with just 2. All the basic operating systems and operating the disk and that kind of thing can be put into 2 ropes. The rest of them are mostly for system kind of stuff, for flight computers. All flight computers, obviously, they filled up all 6 ropes. Sometimes they tried to overflow them, but some of the people last night heard about Tyndall. He was the guy that cut the extra out so we could put it in the computer. Okay, let's take out this thing. Little, oh, you lose those? Oh, that's right.
Eldon,
Yes.
what technology did they use to weld the wires? Was that a spot weld?
Well, I guess it would be called a spot weld. Of course, it depends upon in welding the integrated circuits. These are welded also to the molar board. It was a double prong that came down on the top of the lead like that. Now, does that mean a spot weld? I'm not sure.
Probably, if you flow a heavy current through it, you would melt the copper wires to each other.
Well, they're not copper wires. Everything is more weldable wire than copper. We didn't use that. The wire itself, the interconnection wire, was nickel. And we got, all the components had leads that were either nickel or very compatible welding material. But for one of these wires to a component, I think it was a welding head that sort of clamped it like that.
Yeah.
Right?
Probably passed a heavy current.
Yeah, through it. Okay, now, he just took off. Let me get this again. I wanted to use this to explain the fact that the computer had to be environmentally sealed. So you see here an O-ring around here that went between the 2 trays, so that the 2 trays, when they put together, formed a seal with this O-ring. So all of the internal guts of the computer was in an environmentally sealed container, in effect. And as you see, even though this computer may be close to 40 years old, there don't see much corrosion or anything in these things. So this machine, even though it's been sitting around and in a junkyard and all that kind of stuff, the internal guts looks pretty clean. So until we started taking it apart, it was well sealed. Now, I can't take this. We
decided not to take this.
Yeah. I wanted to explain here this thing right here. See, to plug the ropes into the front, which is the requirement for when it's mounted in the spacecraft, as you saw, this was out to the front. So when we designed this, we even assumed that the may have to change ropes in flight, but at least you have to change or put ropes in during ground tests and before flight. You would change the program from a test type of thing to the actual mission type program. So this had to be plugged in from the front so we could make those changes when the computer was mounted in the spacecraft. So to unravel the wiring, we had to have what was called this tray here, which for some reason I don't know that we can get out, but anyway, it took the wiring from the tray, which we will now go to just a moment. You want to turn these over again and look at the other side. So you might as well turn that one over too. This is the part of the computer that interfaces with the cold plate. So all of the power from the computer, the thermal, has to be dissipated through this plate, in effect, to to the cold plate of the space strip. So we'll take this off now, and you'll be able to see what was called back then, at least, back panel wiring. I don't know what you call it today. But you got to interconnect all these modules some way. So. Yeah, well, he's taking it apart. You can, in this slide, you can see what we're going to see when you take that off. This is the, you're looking at the wire wrap panel for the logic tray, the one on this side. I don't know whether in this day and age people are familiar with wire wrap is or not, but it was an automatic method of interconnecting pins of this nature using what was called a Gardner-Daimler wire wrap machine, which took a punch card to define the program that ran the wires. At MIT, we generated the punch cards, and Raytheon would feed that into their wire wrap computer, and that is what you see, interconnecting all of the modules that we looked at on the other side.
What gauge wire were you using?
Well, you're testing my memory. I won't judge a guess. Is there any experts on wire size that could guess?
30 or 28?
I don't think it was 30. That sounds too small.
I'd say 28. They
Yeah.
used to do a lot of wire wrap.
Yeah.
What is the significance of the yellow insulator?
When we put it down. I really don't know. No, there's no wire going through there, so it doesn't look like it's attached. Is there wire going
No
through?
wire going through it.
The reason for leaving this unpotted was so if there was any design changes in these early machines, we could patch them here, but you don't see many on this one, maybe by serial number 14. Let me put it down, let me look more closely at it. Is there a wire in there? I don't think there is. No, it's just a piece of, here, boy, don't let the QC man see me.
QA in the room?
I think what the purpose of this is just to make sure the wire doesn't come out of their slots in various locations. You see several of them here, just try to hold it.
The 10-inch centers?
Yeah, the pins are 10-inch centers. Then the power buses themselves are right in here. Those had to be put in by hand, of course.
Who are your bypass? And it's
Huh? Oh, there's no bypass.
no.
No.
Just another design.
Yeah, it was in block 1. And it was giving us more trouble than it was worth. So in block 2 we got rid of them, right? Ray? The bypass caps that we had in block 1. You remember? You guys thought you had to have black,
That's right.
right? And they caused more trouble than they were worth.
Could you explain that to the audience a little
No.
bit? Okay.
I get it. Had to do with wanting to have a single point, a single ground, which was the analog way of designing, single point ground. But with the computer, you couldn't do that because you had inductors that just would be way too big. So there was some attempt at making the grounding more ground by putting capacitors. So anyway, those bypass capacitors were a way of fixing something that didn't work. So,
Between the brackets?
they were trying to, yes, they were, my memory is vague on this.
Power to ground.
Yeah, power to ground, so that, because the AC, the high frequency, needed to have a return to low impedance, and it just didn't work. Just couldn't do it. So
I think-
block 2, it was all hard wired, so that the whole machine was one great big ground plane, if you will.
Which violated the mill specs too.
I don't see any bypass caps on this logic module here.
No,
Was there ground
wait,
planes?
that's block 2.
Yeah.
We don't have bypass capacitors.
Was there a ground plane in the multi-layer board?
It's block 1.
Yes.
Block 2 had no
It did have the ground
Yes.
plane.
Pardon me? The ground plane, if you look right here, that ties the signal ground inside here to the frame. See it right there?
Right. And I think Ray just said you're powering ground planes in the multi-layer board?
Right.
Yeah, inside the multi-layer board, there were multiple ground planes.
So you did have capacitance. It was just...
Well, just the slight capacitor that's in the multi-layer board. There was no physical
Sure.
components. One thing, Ray, that might be of interest, I think one of the problems with those bypass capacitors is that their high-frequency performance wasn't that good,
Yeah, there were
Right.
tangible capacitors, and they don't do very well with high frequencies.
right? No,
You didn't have those little chip ceramic capacitors.
not back then, no.
There was something about not being able to use them. You know, they did exist, but
You're right.
What sort of edge rates did you have on your signals? Out of the
Sorry?
what sort of edge rates did you have on the signals out of logic modules? I know that might be pressing things, but
Fraction of a microsecond.
oh, it'd be 30, 40 nanoseconds. There were some pretty good rates at some of the things.
Pretty good.
Depends, yeah.
For that day and age.
Did you have any noise issue getting the core memory sense amps working?
You bet.
Describe some of the chickens that were slaughtered to fix that?
Well, that was I didn't do that very well, but I wasn't the one that was screwing it up. But after a lot of ad hocery, we managed to get the noise. It was in the very few millivolts. So the coincident core memories at the time were not a total black eye, because by that time they already had made the cores with lithium so that they weren't open temperature sensitive, so that this was already advanced technology. And the thing about the core ropes was that there were lots of noise issues, but fortunately once a design worked, it worked, because the coupling was between various wires and went in and out of the cores and the like. So that one, if you get a particular core rope that read ones and zeros successfully, then you were sure that this was going to keep on being what it was not so with the coincident core memory.
Did that change with the program that was wired into the rope?
Absolutely. And so, and by the way, not only that, but the program in the backplane, the noise coupling between all these wire-up lines also changed with a particular logic connection. Fortunately, there are more than one way to get from point A to point B. So there was a program that actually optimized the layout to not put too many wires in any one channel, and also if there was any one place in which the noise coupling was noticeable and a problem, you could take that one wire and wire it somewhere else. So it was not easy.
yeah, I was looking at this when you took the covers off. I saw what, with some of the more modern logic, of just a few nanoseconds, you see a lot of parallel runs and bundles.
Yeah, was that
Wondering what
hand
kind of
wrapped or machine
Oh, no,
wrapped?
it's machine wrap.
Were you fighting a lot of noise issues on these backplanes, these long runs?
Well, not many of them bubbled up to me. The issue that bubbled up to me was a little more serious than this. The first computer, Block 1, of course, when I was put into the laboratory, the laboratory was a temperature-controlled, environmental controlled, all that foolishness room. And when the people walked around the room and touched the frame, the computer would hiccup. So it took quite a bit of effort to figure out what's going on here, and we actually generated what was called a spark. What do we call that thing?
Yeah, that one, I had my fingers dirty on that one. The people came up and said, the computer doesn't like me. every time I walk into the room, it restarts. So Al Hopkins and I finally said, okay, we've got to go down and actually see what's going on. And we didn't have a clue. So we went in there and after a while, we found out that indeed you could walk up there and bump into a chair and it would restart. And after about a week, we finally got it down to, oh, static electricity, how about that? So we got ourselves a Ford coil, and we made something that put a spark about, yay big, about, 4 or 5 inches big. And then we started sparking. This room was a totally closed room with static shielding and a great big bus bar all around it. And we were able to walk into that room and then shoot the spark into the nearest bus, maybe about 30 feet away from the computer. The computer would restart. So then the mechanical folks at Duggan and so forth said, okay, we know what to do, and began basically water sealing the computer. If you make the whole thing hermetically sealed so that you could dunk it in water, that is a good solution to electrostatic discharge. So we went after it, and by the time we got done, we could take that 6-inch spark and spark it right into any place in that computer except the I/O connectors, and it would still work. Now that, I think, is a beautiful thing. But there's a couple of more things about this story. Once we heard about static electricity was a problem, we said, well, maybe other people have that same problem. So we called IBM Federal Systems Division and said, well, do you folks have problems with static discharge in your Saturn computer? Oh, no, we don't have that problem. Well, do you mind if I come with my spark generator and schedule problem? So then I tried class 2, and I said, well, let's see what other computers have that problem. And I went to the guy who was running the IS shop at the time, a man called Dick Russell, great big burly Irishman. And I said, can I come into your Honeywell 1800 and shoot some sparks into it while it's running and see the hiccups or not? And he threw me out of the shop at bodily, so so that was the story.
But one step further, one of the steps we used to solve this problem also was to make the frame signal ground. And that violated the military specs on EMC and so forth. And it shook a lot of people. In fact, on every flight, somebody decided they had to verify the fact that that wouldn't cause some sort of strange loop within the spacecraft. But that helped a lot too in reducing the noise inside. Now, one of the reasons for that is micrologic is very sensitive to RPL, rather, is very sensitive to transient noise. So it's really the problem of the integrated circuits as a result of this. Now, I guess modern technology, the circuits themselves are much more tolerant to noise levels. You're looking kind of great. It must, I think it's more, I think our problem was worse than yours. So,
I think we got some stories to rival that one.
Yeah. My dog is worse, but bigger than yours. Okay, so you see both trays now, and this is much simpler, obviously, because this kind of electronics doesn't require the density of interconnection that you see here.
Hey, Rod, go around to the back of the scanner.
But one thing I wanted to point out here now is that when you saw us pull these two trays apart, you might ask the question, well, how do you get signals from here to there? So right down through the middle here is the connector. And if you go to this one, that's the male connector, and over here is the female connector. And they're all included in the wire wrap down through the middle here. So all of the interconnections between everything was wire wrap. And likewise, this thing which we didn't take out is the same way. Down on the sides here, right down here and over here, is the connections that go into what we call a rope tray here. And then I think this was done by hand wiring, I'm not sure. But to connect those signals now to the ropes that come up through here and into the backplane wiring back in here for the ropes that are plugged in here. So I think that was hand wiring, but I'm not sure of that. Because the Darrow Gardner Daimler machine only works on a flat plane like this. Now, unless there's some more questions on this kind of thing, I would like to go on to a disky. Now, unfortunately, oops, that didn't show very good.
Yeah, can we turn the lights off in the
Yeah.
back room, just so anyone will figure out how to do it?
Right. In the Block 2 disky, that it wouldn't be significant at all. But I do have here the picture of the command module's, a piece of the command module's main control panel and the disky that sat in there. Here is one of those diskies. You saw the other one in the lower equipment room. The next slide, please. Now this shows you the various pieces of the Block 2 disky. If any of you that saw the Apollo 16 disky, that disky in flight, there were no all-eight plate. That whole problem of contamination in parts was not only interesting but very scary. In the flat packs, we worried all the time about the potential loose particles in there that was going to short. We did experience some in ground testing. There was no real good way to screen them. As Klein mentioned, that Minuteman got into trouble with those things. That was a very serious problem in the early integrated circuits and transistors. So we were constantly worried about maybe there's contamination in all of these gates that could give us a problem in flight. But, pardon me?
You did testing that? Is that how did you rattle them?
Well, we tried that, but it didn't seem to be effective. We used X-ray to X-ray everything. We tried many different things to come up with a solution or a screen. It's what you're really looking for, to screen out the potential ones. And there was nothing we were confident in. Now, I haven't said anything about the testing we did on the integrated circuits, but we developed what is termed screening tests nowadays and age, but we weren't confident screening. So we did some visual inspection on every lot, lots of tests. But as far as contamination is concerned, we did visual inspection by actually destructive opening the can and looking at them. And if any of those that we opened had contamination, that whole lot would be rejected back to the vendor. No question at all, they would go back to the vendor. There were other failure modes of a similar nature that we would cause the lot to be rejected. So it was that kind of technique that we used to force the vendors to do a good job. And with history behind us, we did a good job. And this relay situation is the only experience we had of what we think was a contaminated relay. And we had lots of problems in the relays too, with in vibration on the ground and those kind of things before flight of contamination inside. But we don't think, with the experience of that one disky, that parts seem to float around inside. Now, the previous speaker talked about that abort button, and on Apollo 14, it was pretty clear that had contamination in it. And that was floating around apparently, because every so often they would get an abort signal before they started the descent. And incidentally, it was Don Iles who came up with the procedure to ignore that problem in the abort button. And that's interesting too. As he said, that was radioed up to the astronauts and they keyed it in. That proves that they didn't trust the computer, because very early my friend Ray Alonzo over here came up with the idea of these key codes when you plug the key, and we had an uplink which you could have a ground disky just like this thing and key it on the ground and send it through the uplink and put it in the computer. And you could do that through paper tapes and all kinds of other input things. But on that flight, Apollo 14, they could have put that up through the uplink automatically and loaded it into the computer. But they didn't trust that. They had them radio it up, voice, to the astronaut, and the astronaut keyed it in manually. They wouldn't trust the digital technique. I think I'm done with all of this, unless there's some more questions.
Are you able to do a post-mission analysis to confirm some of these contamination problems?
Lights on.
We were never allowed to touch anything that came back. No, we never did post-analysis. We never had a failure. And as far as I know, they didn't do anything out of the Apollo 12 disk, did they? There was hardly any point to it. You came back, okay, what difference does it make? I mean, we were interested in going to the moon, not figuring out whether these things worked or not.
Take experience generally that the astronauts didn't trust the computer.
The astronauts didn't like the computer. I'm glad John Young isn't here. Every time I had anything to do with the astronauts, they didn't want much to do with the computer at all. The only one that had any interest or showed any interest in the computer is Dave Scott. He was resident of the lab for a while, and he was very interested in the computer. But all the rest of them wanted nothing to do with it. Is that right?
Pretty much.
McDivitt was the next best, but he was more interested in the guidance system itself, too. Yeah. But Dave Scott worked with us. Actually, he signed the drawings for the Disky as the astronaut approval of all those lights and stuff. You know, I didn't cover that very well, but the Disky was a very technically difficult job, the design of that. The pressure of the keys had to be just right, so the astronauts, well, first of all, they were supposed to operate it while they had the gloves on. And, of course, you're in space. You don't want to have to press this thing and land up on the other side of the spacecraft. So the actuation pressure had to be just exactly right. The Yale panels were supposed to be other colors, but fortunately you couldn't get anything but green back in those days, so they had to live with the green panel. Lots of things of that nature, which was the human factors type of inputs on the thing, made the Disky very difficult to design. And I have to give Raytheon credit for actually mechanical designing the box that you saw there. We did the basic internal guts of the Disky, but they made that design so it would fit in that size and have all those good things about it necessary to keep the astronauts happy, or the human factors types, whichever one it was. Are there any other questions? Yes.
How many gates in your logic module, and how many bits was your
In this module, there's 240 gates, 120 flat packs. Each flat pack had 2 gates.
How many in the entire?
There's 24 modules. Maybe you can multiply. I don't have my computer. I wanted to change the subject slightly.
One more question.
Oh, okay.
Did you build your flip-flops out of the NOR gates, or
Yes.
did Philco give you
No,
NOR gate?
no. It was one logic gate. Period.
Just the NOR.
And the engineers had to design with that. Absolutely. That's a different question. I mean, engineers didn't like these things because they couldn't get in there and tweak them. They couldn't do their thing. The circuits in the memory, most of the engineers didn't like. I mean, they didn't want to. Oh, pardon me, I'm off base. Most engineers back then wanted to design and tweak their resistors and all that kind of stuff to make their circuit work the best, you know. And when you come to something like integrated circuits, the engineer's out of a job, in effect. He can't tweak anything. He just can interconnect it. So that was one reason why integrated circuits didn't catch on very rapidly, is that the engineering community just didn't like the things. It was taking their job and putting it in the semiconductor industry. And when you got to microprocessors and so forth, that even got worse, I think. Unless there's some other questions, yes.
I'm a little confused by all the pictures of the diskies that I've been seeing, both your presentation and Frank's presentation, because the positions of the indicator lights don't seem to me to correspond to actually to the pass flow configuration.
What?
The C key is replaced by a standby key. I've seen these pictures before, and I'm wondering as to what exactly they're used for.
The diskey that was shown before is exactly the same as what I showed here. If you saw the diskey on the main panel with the lights up, that should match what he showed you.
Well, we can go back. What? One direction. I'm sorry, the other direction, I believe. Picture of the diskey. I think that also has the standby button. Later on, that was
oh yeah, there's a button.
Yeah, and the indicator lights too.
Yeah, those bulbs can change to as well.
So this represents an early configuration.
What are you saying?
Okay, the diskey. The question this gentleman is asking is that there was a small evolutionary change where this key was replaced by one labeled proceed. There was no longer a standby. And some of the other lights here were also either deleted or modified.
Well, yeah, some of these were changed because of, like in the lamp, you would have different kinds of status lights, this is called caution status lights. And in the lamp, this was slightly different than in the command module. So you have this is pluggable, and you put in a target there.
For example, in the LED diskey, you would have two lights for your landing radar altitude and velocity clip. And of course, on the command module, you wouldn't need them. So, although the base systems were essentially identical, there were few little modifications.
So the point is that this is an early configuration.
It was probably right before they freeze the design.
I rejected the word early. This is here, very likely got used something.
Okay, so I have one more question.
Okay, this will be the last one, then we'll have a break. How's that sound?
I got something more I want to say.
Oh, okay. All right. Okay, one more question.
From me or from someone?
Well, if you can briefly, go ahead.
Okay, well, some of the take the key rel indicator in a command module would be in a different position. Now, would that be seen by the AGC as the same bit on the same I/O channel?
Yes.
Okay, even though it's physically moved to a different position.
And you'll also see that there's a function warning or the status link. There's a tracker one. The tracker was deleted, so you won't see that as far.
The computer had two outputs and input registers. And so lower click fade diskey going to one, and the main panel display going to the other. So the communications with the two disks were different internally, so software is different. Well, I wouldn't do. Can I take a few more minutes?
Yeah, go ahead.
The previous speaker talked about this Apollo 11 situation, and he made the statement that the computer was working correctly. It did not fail like is reported, and I verified that. But I think it's interesting what happened in Apollo 11. Not the details of what was going on in the computer, but first of all, like he mentioned, a procedure was changed, which was not intended in the beginning. I'll call it the specifications, to have the the rendezvous radar on during landing. That was not a procedure that was worked out at the beginning in the software or anything. I don't know when that procedure was introduced, but it was a change. So that's error number. I'll call that an error, because it was introduced and not properly evaluated. That's an error. Now, second, the software guys, they were interested in whether the computer was getting overloaded or not while they were testing on the ground. So they wrote a procedure, and this is where the previous speaker had it wrong. The software guys wrote a procedure which detected whether the computer was setting aside low priority tasks, which the wait list was designed to do. If the computer got overloaded, it would set aside one task and do it when it had time. And so the software guys wanted to detect if that was happening. So they put in a special set of programs which would detect that feature and display it as he mentioned for testing on the ground. Now the intent was to remove that because it's not necessary in flight. So they failed to do that. So that was an error. So those two errors is what resulted in that problem in Apollo 11. Am I right?
Oh, I didn't realize about the second one.
Yeah. Well, I didn't learn that until the celebration of the 25th anniversary at the lab. A very young software engineer, very young back then, was working on the program, and that's what he said they did. That's why they put that in there. But from my point of view, the computer was designed to priority system and to set aside those, so that definitely wasn't needed in flight, because that's the way it was supposed to operate.
I think we'll take a very short coffee break and we'll come back and we can take more questions and then Ray can talk some more. So don't go too far away, but have a little break and maybe in 10 minutes. So it is, let's say, thank you.
I missed a very important point here. The man that we should honor for all this good stuff here you've just seen that got this thing from the junkyard is my friend here, Jim Locke. He's the guy that you can give credit, because I don't know of any other private individual that has an Apollo computer. And he also has a few other modules and types of things here that might be of interest to you.